Welcome back, Apologia 8th grade Physical Science, week 21, day 2. Textbook pages 353 to 357, notebook pages 296 to 301. Wavelength and frequency. All electromagnetic waves traveling in a vacuum travel at the same speed, the speed of light. But this doesn't mean that all electromagnetic waves are the same. The wavelength and frequency of different electromagnetic waves vary, even though their speed is the same. So they will have the same speed, they will have different wavelengths, and they will have different frequencies. Just like with sound waves, the speed of electromagnetic waves is the wavelength times the frequency. Remember that frequency and wavelength are inversely proportional, so as one gets larger, the other will get smaller. Also remember that the speed of electromagnetic waves is constant, 3 times 10 to the 8th meters per second. And we represent the speed of light or any electromagnetic wave with the symbol C. C equals 3 times 10 to the 8th meters per second. So if you know the wavelength of an electromagnetic wave, you can calculate its frequency using equation 9.1. V equals the wavelength times the frequency. The dual nature of light. Scientists know that electromagnetic radiation, such as light, travels as a wave, but they also have evidence that electromagnetic radiation behaves like a stream of particles. So then which is it? Well, let's look at what scientists have discovered about how electromagnetic radiation behaves. The first serious scientific investigations of light were done by none other than Sir Isaac Newton. In 1704, Newton published a book called Optics, in which he reported the conclusions of his research on light. In this book, Newton concluded that a beam of light behaved the same as a stream of particles that all moved in the same direction. This came to be known as the particle theory of light. According to this theory, light comes in little packets. We cannot see the individual packets of light because they are simply too small to distinguish. Thus, just like a stream of water is really composed of individual water molecules, a beam of light is really composed of individual light particles. The Dutch mathematician and physicist Christian Huygens, who lived at the same time as Newton, disagreed with Newton's conclusions. He considered light to be a wave. He published his own work in which he could explain all of Newton's experiments, assuming that light was a wave and not a particle. This was called the wave theory of light, and it was largely ignored at the time. In a few years, however, scientists began to do experiments that indicated light does indeed behave as a wave. And as a result, by the early 1800s, most scientists believed in the wave theory of light. In 1801, the English physicist Thomas Young showed in an experiment that light behaved like a wave. And to understand how he did that, first look at the vibrations created in water by raindrops. So they just make little droplets. Here we have figure 10.5. Notice what happens when the vibrations from one drop run into the vibrations from another drop. So you could see the rings, or the waves, are sort of coming together or overlapping even. When these waves meet each other, they interact. The interaction of waves with other waves is called wave interference. When two waves traveling in opposite directions meet, they pass through each other, which affects their amplitude. How the amplitude is affected depending on the type of interference. There are two types of wave interference. There's constructive and destructive. All right, so let's take a look at this. We have wave A coming this way, and we have wave B coming this way. So when they hit, they sort of add together, so it sort of doubles the amplitude. So we have the amplitude of A plus the amplitude of B coming together right here as they pass each other. So we have B going this way. So as they pass each other, we have B going this way, and then we have A going this way after the interference. All right. When the crest of one wave overlaps the crest of another wave, constructive interference occurs. Notice that the waves combine as they pass through each other, and the amplitude of the combined waves is greater than the individual wave's amplitude. When the crest of one wave overlaps the trough of another wave, destructive interference occurs. What happens to the combined wave then? The amplitudes cancel each other out, and the resulting wave has an amplitude of 0. All right, so if we have this A and the crest of this A is the same as the trough or the amplitude of this B wave, as this one goes this way and this one goes this way, they just cancel each other out. They have the same, equal, and opposite amplitude. So then here we go. B passes by over here and A passes by over here. So when the crest of one wave meets the crest of another wave traveling in the opposite direction, constructive interference occurs. If a crest of one wave meets a trough on another wave, destructive interference occurs. So how does this help us understand how Young determined that light was a wave? Well, where waves interfere, they create interference patterns. Remember, where crests meet crests, there will be larger amplitudes, and where crests meet troughs, there will be no amplitudes. This creates a pattern. You can see this happen in the oceans, where the interference of waves coming from opposite directions creates a phenomenon known as square waves or the cross sea. You can really just see how it looks like they're squares. It's pretty cool. Just so you know, square waves are rather rare. However, if you should see this while at the ocean, get out of the water as soon as possible, because this phenomenon causes dangerous swimming and boating conditions. Now, let's talk about Young's experiment. If light behaves as a wave, Young expected to see an interference pattern as the waves overlapped. If light did not behave as a wave, then he would expect to see the light travel in a straight path. All right, figure 10.8a. So we're talking about this setup over here. If light behaves as a wave, Young expected to see an interference pattern as shown in A. The setup for B. If light does not behave as a wave, Young expected to see a pattern similar to B. And over here, when Young produced the experiment, he observed that when light is passed through slits, it produces an interference pattern confirming that light behaves like a wave. So Young set up 3 boards, one with a single slit in it, one with a double slit in it, and a solid one to be a screen. He then passed a light beam through the slits to see what would show up on the screen. Figure 10.8c, this one, shows Young's results. He observed alternating bands of light and dark. In other words, Young observed an interference pattern. The bright band on the screen showed constructive interference, and the dark band showed destructive interference. Therefore, Young's experiment showed that light does in fact behave like a wave. By the mid-1880s, most scientists were convinced of the fact that light is a wave. However, in 1887, Heinrich Hertz, the same scientist that the frequency unit is named after, discovered something puzzling. Hertz discovered that when blue light hits the surface of a metal, electrons were emitted. The brighter the blue light that hit the surface of the metal, the more electrons were emitted, as shown in figure 10.9. The interesting part was that if bright red light hit the surface of the metal, no electrons were emitted, and this is called Photoelectric Effect. So this shows that electrons are emitted from metal. So when blue light hits the metal, electrons are emitted. Even here, when one blue light hits it, we have an electron being emitted. However, when red light hits the same metal, no electrons are emitted. So the photoelectric effect is a phenomenon that occurs when light shined onto a metal surface causes the ejection of electrons from that metal. It was observed that only certain frequencies of light are able to cause the ejection of electrons. Scientists could not understand how blue light could cause this, but red light could not, if light behaves like a wave. So that put a little bit of doubt into the fact that light only travels as a wave. Then, in 1905, Albert Einstein proposed a new theory often called the wave-particle theory. The wave-particle theory explains that electromagnetic radiation, including light, could behave both as a wave and a particle. Well, how can that be? Well, remember the quantum mechanical model of the atom from Module 3. That model explains that when the electrons return to a lower energy state, they release energy. Remember climbing the ladder from one energy state to the next? Einstein argued that the energy released from the electron returning to a lower energy level was given off in packets of energy. We now call such packets of energy photons. Photons do not represent a fixed amount of energy. Rather, each photon's energy depends on the frequency of the electromagnetic wave. The greater the frequency of the electromagnetic wave, the more energy each of its photons has. As it turns out, blue light has a higher frequency than red light. This means that photons of blue light have more energy than photons of red light. Blue light photons have enough energy to cause electrons to be emitted from the surface of a metal. Red light photons, on the other hand, do not have enough energy to cause electrons to be emitted from metal surfaces. This is because the frequency of the red light is low. According to Einstein, a photon is a packet of energy released when an electron returns to a lower energy level. After release, the photon travels outward as a wave. Then, as waves of photons travel through space or matter, they make up electromagnetic radiation. Since Einstein proposed this theory, there has been quite a bit of evidence gathered to support it. For example, using modern technology, scientists performed something similar to Young's experiment. They used a very sensitive camera to take photos of laser light passing through two slits. The photos showed tiny pinpoints of light pass through the slits, seeming to indicate that light consists of particles. However, if they left the camera lens open for a long time, the pinpoints of light formed bands, just like interfering waves. It shouldn't surprise you that this is called the quantum mechanical theory of light, and it is currently the accepted theory on the nature of light. Since this can seem quite confusing, let's sum it up. All right. This is very important. This would probably also be a test question. Light is composed of little packets of waves. Each individual packet can be thought of as a particle called a photon. So you could say light is composed of photons. At the same time, however, since each packet is composed of electromagnetic waves, light can also be thought of as a wave. Thus, light will sometimes behave as a particle, and at other times it will behave as if it is a wave. Since waves within a photon are electromagnetic, there is no need for atoms or molecules in order for light to travel. And as a result, light can travel through any region of space, regardless of what occupies that portion of space. All right, on your own, what produces an electromagnetic wave? What do all the electromagnetic waves have in common, and what makes electromagnetic waves differ from one another? So the vibration of the electric charge, like an electron, produces electromagnetic waves. All electromagnetic waves have the same speed, but they differ in frequency and wavelength. Suppose a photon, on your own 10.2, suppose a photon is traveling through air. If the particle suddenly hits a lake, what will happen to its speed? All right, so go back to the table. Light has a speed of 220 million meters per second in fresh water, which is slower than the speed of light through air. Thus, when the photon hits the lake, it must slow down. And remember, the speed of light travels slower in a solid than it does in a gas. On your own 10.3, how does photon energy relate to frequency, and what experiment first showed this? The greater the frequency of an electromagnetic wave, the more energy each of its photons has. This is shown in the photoelectric effect when, unlike blue light, the frequency of red light is low, so the photons do not have enough energy to cause a metal to emit electrons.